Hi everyone. In this video, we'll look at two important properties of the Riemann integral. The first will be an algebra of the Riemann integral theorem, which will establish some important basic properties of integrals, just as we've seen algebra of derivatives and algebra of continuity and algebra of limit type theorems previously in this course. And the second property we will look at will be the fundamental theorem of calculus. So to begin, we want to start with theorem 2.39, algebra of the Riemann integral, which says let f and g be Riemann integrable functions on the closed interval ab, and let c be some real number. Now, there are actually four parts to this theorem. The next screen will have the other two on here, but I've separated them out on purpose. The first two properties. So if I look at the first one here, this says that f plus or minus g is integrable on the closed interval ab, and the integral from a to b of f plus or minus g of x dx is equal to the integral from a to b of f of x dx plus or minus the integral from a to b of g of x dx. So again, this really says that if f and g are both integrable, then f plus g is integrable, or f minus g is integrable, and the value of the integral of f plus g is just the integral of f plus the integral of g. Same for minus. The second theorem here, or the second part of this theorem rather, says that if f is integrable, then c times f, where c is a constant, is Riemann integrable on the closed interval ab, and the integral of c times f dx is just equal to c times the integral of f. So taken together, these actually both say, these say combined, that the Riemann integral is actually a linear operator on functions. So if I take, for example, my domain to be the set of all continuous functions, since I know those are Riemann integrable, then this is a linear operator from that set of continuous functions into R, right? These integrals spit out real numbers. So because I can break them up over sums and I can pull out constants, this is actually a linear operator. Now, these look similar to claims we've seen about other things, right? So we've seen that you can break up a derivative over a sum. You can pull a constant out of a derivative. You can do the same thing with continuity and limits, right? If f and g are continuous, then f plus g is continuous. You might notice, though, that we are missing some things. We're missing things about multiplication and about division. And that's, in fact, because it's a little harder to state results in that case. It's a little harder to say, for example, that if f and g are integrable, then f divided by g is integrable, for example. In fact, that's not true, as I've stated it. So we really have these two properties that are really, in sort of the strictest sense, algebra of Riemann integral type properties. We've seen these in the other sort of algebra of whatever theorems. Now, the next two parts, so again, same hypotheses. I'm just adding parts 3 and 4 here. So part 3 says if c is some value between a and b, strictly between a and b, then the integral from a to b of f is equal to the integral from a to c of f plus the integral from c to b of f. So the picture we want in our minds here, right? I have some function, and right, I have this here, and we want to be a little careful. This is actually saying sort of a couple of things implicitly. So my assumption is that f is Riemann integrable on AB. So, right, I can think of this pink area here, right, sort of representing the integral from a to b of f. And what this is saying is that if this integral exists, and I take any value c between a and b, so let's say I pick c maybe right here, okay, then this integral, the integral from a to b of f, is equal to the value of sort of maybe I'll put some dots in here. So this yellow integral, which is the integral from a to c of f, plus this blue integral, which is the integral from c to b of f. Now, implicit in that statement is the fact that if f is integrable on the entire interval ab, then it's also integrable on the interval ac and integrable on the interval cb, right? In fact, this is true more generally. If f is integrable on ab, then it's integrable on any subset of ab, on any closed interval subset of AB. Um, so but this is actually saying both that it's integrable on each of these intervals, and the sum of these two gives you the value of the full integral from a to b. Okay. Now, the last piece here is sort of a comparison type property. So it says if f of x is less than or equal to g of x on the closed interval ab, then you can order their integrals in the same way. Then the integral from a to b of f must be less than or equal to the integral from a to b of g. So each of these, broadly speaking, when I think about it, each of these are properties that I could prove for finite sums. So if I were to just, for example, take like the last property here, I'm not going to actually prove that one. So let me sort of take that one. If I was just dealing with a sum, right? The way a lot of these proofs work is you sort of think about, well, if I took some sort of sum, either a Riemann sum or an upper sum or a lower sum, whatever kind of sum I took. So let's say I took a Riemann sum for f, f of ck times delta xk. This would certainly be less than or equal to, if I replace each of these with g of ck delta xk, right? This works for sums. If f of x, so if f of x is less than or equal to g of x, then that implies this. And then the idea is that somehow, and I'm going to put sort of squiggly equal signs here because the real analysis is in how do I make this sort of more rigorous. But the idea is this should be approximating the integral from a to b of f of x dx. This should be approximating the integral from a to b of g of x dx. And so this should be true, right? So the idea of a lot of these proofs is essentially you establish that it works first for sums, right? And then once you know it works for sums, you try to prove somehow, I would say, this isn't magic, right? It's analysis, right? But we need to use some analysis, usually via the definitions of these objects, to then prove that it actually holds for the integral, right? So many of times the depth comes from how do I do the analysis to prove that this thing that holds for sums is often fairly trivial to show it holds for a sum. The real challenge comes in how do I prove that it works for the integral itself. Okay. So to see an example of that, I want to actually go back. We're going to prove one, okay? And we're going to prove it in the case of plus. The case of minus is not substantially different in any way. So I want to prove that if f and g are both integrable, then f plus g is integrable, and the integral from a to b of f plus g is equal to the integral from a to b of f plus the integral from a to b of g. So let's look at a proof of this. Okay. So again, if we think of this sort of just abstractly for a second, right? If I think about approximating these things by sums, right, fundamentally, I feel like sorry, this should be delta xk. Right, this is equal to And I can break this up like this feels like this should work. It works for sums. I feel like it should work um, for integrals as well. All right. So in order to do this, right, we are going to need to first, I know this will be shocking, we're going to need an epsilon. So let epsilon greater than 0 be given. Now we know that our functions f and g are Riemann integrable. Okay. And so since f and g are, and I'm going to use this Ri to just stand for Riemann integrable. So since f and g are Riemann integrable, uh, then there exist partitions. I'm going to have two partitions. I'm going to call them P sub f and P sub g, such that, oh, sorry, these are partitions of AB. Such that I want to choose my partition P sub f such that if I take an upper sum over the partition P sub f of f, that is strictly less than the integral from a to b of f plus epsilon over 2. Now let's understand why I can do this. I know that my function is Riemann integrable. Because it is Riemann integrable, the supremum over all partitions of the upper sums, sorry, the infimum of the upper sums. So the infimum over all partitions of the upper sums is equal to what we call the upper Riemann integral, but because it's Riemann integrable, that's actually equal to the value of the integral. So each of these, right, I can always pick a partition that will get this as close to this value as I would like. Now, these upper sums are always going to be a little bit bigger than the actual value of the integral. Okay, so I can choose this so that it's a little bit less than the integral plus epsilon over 2. If it helps to reformulate this to your understanding, you could think of this as I'm choosing my partition such that this difference is less than epsilon over 2. This is always going to be a little bit bigger than this, right? But because the infimum over all partitions of this is equal to this, I can get this as close as I would like by choosing the right partition. So I'm going to choose a partition P sub f so that this upper sum over this partition of f is within epsilon over 2 of the actual value of the integral. All right. Now I'm going to do something similarly with my partition P sub g. So I'm going to choose that so that the upper sum is less than the integral from a to b of g plus epsilon over 2. Okay. And you might be wondering, well, why epsilon over 2 there? Well, we're going to add some things together. Eventually, we'd like them to be less than epsilon. We're going to want that to be epsilon over 2. Okay. All right. Now, I'm going to let Q be the union or the common refinement of these two partitions. So I've got two partitions of A and B, or sorry, of the interval AB. I'm going to take and I'm going to throw all those partition points into one big partition together. Okay. So this partition Q contains all the points in the partition P sub F and all the points in the partition P sub G. Okay. If I do that, now what I want to do is look at the upper sum over the partition Q of F plus G. Okay. Now, the first thing I'm going to note here, just think about what is this by definition? By definition, this is the sum k equals 1 to n of the supremum. So I'm going to write out actually that capital M sub k we normally put here. This would be the supremum over x sub k minus 1 to xk of my function, but my function here is f of x plus g of x times delta xk. Now, this supremum, I can break it apart. If I do that, I'm going to make, so I'm going to rewrite this as the supremum of f plus the supremum of g. But when I do that, I potentially make it larger. Why? Just focus on this term. That nothing's going to change with the delta x term. Just focus on this term. This is the largest value that the sum of these two functions take. But here I'm assuming that I'm looking at f of x plus g of x. And I'm looking at everything at the same x value, right? And so there's like maybe f is really high at one point and g is really high at another point. But when I add them together, right, I have to be adding them at the same x value. So what's going to happen here is when you break this apart, so this is going to be the supremum over the same sets. What happens here is now you're looking at the x values independently of one another. So now you could just look at the largest value that f ever attains and the largest value that g ever attains and add those together. They don't have to occur at the same x value anymore. So that gives you less than or equal to. And again, I'm going to drop some of the subscripts here so we can focus on the idea. But this now I can break up. This is a finite sum. So this is the sum of the supremum of f times delta x plus the sum of the supremum of g times delta, sorry, these are delta xk's. Okay. And now notice that this really is the term we would expect to see in an upper sum for f, right? So this is actually equal to the upper sum over the partition Q of f plus the upper sum over the partition Q of g. So what we've done essentially is we've been able to say I can break up this upper sum over these two functions, but I'm going to get a less than or equal to. Okay. All right. Well, now once I do that, I can actually also swap out f. So here I can swap out the partition Q for the partition P sub f. Now why? Q was a refinement of the partition P sub f. It contains all the points of P sub f plus some other ones. Okay. And remember before we discussed if I refine a partition, my upper sum is going to get smaller. So this is a finer partition. It has more points in it. So the upper sum here is going to be smaller than here. Okay. Similarly, I can do the same thing here. Upper sum of P sub g. Again, Q is a refinement of P sub g. So the upper sum of P sub over the partition P sub g will be greater than the upper sum over the partition Q. Great. Now, I know something about these. I chose these in a very particular way. Okay. So I chose this so that this was strictly less than the integral from a to b of f plus epsilon over 2. I chose this so that this was strictly less than the integral from a to b of g plus epsilon over 2. And now, and I know I'm getting close to the bottom here, I'll be mindful of that, but this is just the integral from a to b of f. Make sure that all picks up. Plus the integral from a to b of g plus epsilon. So if I look at this, what I have shown is that there is a partition Q that is within epsilon of this value, which is the integral from a to b of f plus the integral from a to b of g for every epsilon, right? This worked for an arbitrary epsilon, okay? So what I have is finish over here. So therefore, if I look at the upper integral from a to b of f plus g, right, this has to be less than the integral from a to b of f plus the integral from a to b of g plus epsilon. Now, why is that the case? This upper integral is the infimum of all of these things. What I've shown is for at least this one partition, Q, the value of this is strictly less than this integral from a to b of f plus integral from a to b of g plus epsilon. So certainly this thing, which is the infimum of all of these things, must also be less than that. But now if this holds for all epsilon greater than 0, then it must also hold when epsilon is equal to 0. And therefore have the integral from a to b, sorry, the upper integral from a to b of f plus g is less than, less than or equal to the integral from a to b of f plus the integral from a to b of g. All right. Now, you can flip all of this around and do the proof again for lower sums. So do everything for lower sums, okay? If you do lower sums, that's going to give you something about a lower integral, and you'll get similarly, we can show that the lower integral from a to b of f plus g is greater than or equal to the integral from a to b of f plus the integral from a to b of g. Okay. Now, how did these two things then combine? So maybe I'll erase a little bit over here. Okay. So now what I have here, right? If I look at my upper and lower integrals, right, I know that they are ordered, right? The lower integral is always less than or equal to the upper integral. So what I have, if I start here, is I have that the integral from a to b of f plus the integral from a to b of g is less than or equal to the lower integral from a to b of f plus g, which has to be less than or equal to the upper integral. Remember, these things always exist. The upper and lower Riemann integrals always exist. But this thing is less than or equal to the integral from a to b of f plus the integral from a to b of g. Well, notice, right, these are the same, right? So the only way this could hold is if both of these are equal, and that means that this is integrable and it has this value. So, and hence the integral from a to b of f plus g, it exists and is equal to the integral from a to b of f plus the integral from a to b of g. Okay. Now again, no, I want you to notice that the whole sort of point here was that we proved something for sums and then we carried it over via some sort of epsilon argument to something about integrals. Okay. That's how the vast majority of these types of proofs work. So we will not prove the rest of them. I may give you one of them for a homework assignment, but I'm not going to spend the time to prove all of them. Again, they're sort of difficult to write out in many cases because again they're sort of technically demanding. But the fundamental idea is usually not too hard because the fundamental idea again often is just, well, it works for sums. It ought to also work for integrals. I think it's getting close to time. I need to go. I need to get some new cleaning cloths here. They're starting to carry over quite a bit of stuff. Okay. All right, so we won't, like I said, we won't go through and prove all the rest of those algebra of limits or algebra of Riemann integral properties, but hopefully this gives you some idea of how those sorts of proofs go. The last theorem that I want to prove in this video is the fundamental theorem of calculus. The fundamental theorem of calculus, typically when you see it in a calculus course, you see it and there's sort of part one and part two. We're going to focus here. This is really the fundamental theorem of calculus part two, although the ordering isn't even always standard. And it says the following. If capital F is a differentiable function on the closed interval AB, and little f, which is defined to be the derivative of capital F, is integrable on the closed interval AB, then we can express the Riemann integral of f from a to b as the difference between capital F of b minus capital F of a. Now, I haven't done a survey, but I would guess that if you went and polled a bunch of students who've just learned, the first little bit of integration, and you asked them to define what the Riemann integral is, many of them would tell you that this is the definition. Now, that's wrong, okay, but there's a reason for that sort of misunderstanding. And the reason for that misunderstanding is that this is an incredibly powerful tool for actually computing integrals by hand. So powerful that many students just begin to see it as the definition. It is the way that they always deal with these types of integrals. They never actually write down some Riemann sum and take limits. But like, that's not how we calculate these things. This fundamental theorem of calculus is how we integrate them. But of course, it's a theorem. It's not a definition, right? And it's a really powerful theorem, not just because it's really computationally useful, but if we think about what's going on here, on the left-hand side, we have the Riemann integral of some function f. Now, it's not really just any function. It's related to this function over here, right? This function little f is the derivative of this function capital F. But what this says is, on the left-hand side, we have this Riemann integral, right? It's, depending on how you want to think about it, it's some sort of, infimum of upper Darboux sums over all possible partitions. It's sort of some sort of limiting thing of sums. On the right-hand side over here, we just have this difference, and the only relation between these two functions is the derivative, right? That little f is the derivative of capital F. So what makes this the fundamental theorem of calculus is that it's actually at a very deep level relating integration, right, this Riemann integral, with the derivative operator, right? The fact there's this relationship between capital F and lowercase f. So it's the fundamental theorem of calculus because it takes these two concepts that, from the definitions, ought to have nothing to do with one another, right? There's no reason that this thing that's defined in terms of upper and lower sums and infimums and supremums should have anything to do with a derivative, which is defined as a limit of a function, of sort of some secant line type things. There's no reason on the surface that these two things should have anything to do with one another. However, what the fundamental theorem of calculus tells us is they are related in a very sort of intimate way. Okay. Now, it actually turns out that the proof of this is quite slick, and I think in a lot of ways quite beautiful. It does obscure some of that connection because a lot of the derivative stuff comes out of a clever application of the mean value theorem. So we'll talk a little bit more about that as we go. But let's look at the proof of the fundamental theorem of calculus. So let's start. What we first are going to do is we're going to actually start with the right-hand side here. And we're going to make an observation about sort of some arithmetic tricks we can do regardless of what partition we have. Then we'll actually choose a particular partition, we'll apply that arithmetic trick, and then we'll see that the sort of using the mean value theorem, the result that we'd like just falls right out. Okay. So for any partition, so here's proof. For any partition P of the closed interval AB, if I look at f of b, capital F of b minus capital F of a, well, the first thing I could do is I could write this as a sum So I'm going to write this as this sum, k equals 1 up to n, of f of x sub k minus f of x sub k minus 1. And you might be saying, wait, that I don't see how that works. This is what we call a telescoping sum. So if I start writing out the terms of this, when k is equal to 1, I would get f of x1 minus f of x0. When k is equal to 2, I'd get f of x2 minus f of x1. When k is equal to 3, I'd get f of x3 minus f of x2. Okay, I can keep going. Eventually, I'd get a f of x sub, say, n minus 1 minus f of x sub n minus 2. Plus my last term would be an f of x sub n minus f of x sub n minus 1. Okay. Now, it's called telescoping, right? Because notice the f of x sub 1 here, there'll be a minus f of x sub 1 here, they'll add to 0. F of x sub 2, there'll be a minus f of x sub 2 here. They'll add to 0. F of x sub 3, there'll be a minus f of x sub 3 in this next term. And everything's going to cancel out. This minus f of x sub n minus 2 would have canceled with a term here. This f of x sub n minus 1 will cancel with a term here. And what you'll be left with at the end of the day is f of a minus f of x sub 0 plus an f of x sub n. But remember, these x values are points in a partition. And x sub 0 is your left endpoint. X sub n is your right endpoint. So this is just minus f of a plus f of b, or f of b minus f of a. Okay, so it's easier to see why this is equal to this sometimes than going the other way. But we want to actually start here and rewrite it in this telescoping form. All right, great. Now, how am I going to use that? Now, this is where I'm going to use the mean value theorem. Okay, so if I look at this quantity here, and I think about applying the mean value theorem applied to the function capital F would say f prime of, say, t sub k. So if I look at the function f on the interval x sub k minus 1 to x sub k, right, I would get this. Okay, so this is just applying the mean value theorem would say there exists a tk in between x sub k minus 1 and x sub k, so that f prime of tk is equal to this difference quotient. Okay. And if I look at this, I want this piece here, and this written down here, this is really just delta xk. So this would actually give me that f prime of t sub k is equal to, or times, sorry, delta x sub k is equal to f of x sub k minus f of x sub k minus 1. But also notice this capital F prime, that's what we're calling little f. So that actually gives us that little f of t sub k times delta x sub k is equal to this difference. So what I'm going to do is I'm going to replace this difference equal to the sum k equals 1 up to n of f of t sub k times delta x sub k. Well, remember, this t sub k comes from the mean value theorem. So each t sub k is in the interval x sub k minus 1 to x sub k. Okay. Now, again, I can do this for any partition. Okay, this works for any partition. I can do this. And you start to notice that, oh, wait, that thing on the right, thing on that far right line, this is starting to look like, this looks like a Riemann sum. Right? This looks like a Riemann sum for the function f over a partition of the interval AB. Right? So maybe, maybe there's something going on here. Maybe this is actually equal to the value of the integral. Okay, so now what we need to do is we need to do the sort of analysis bit of it to show that, okay, this is actually, this sort of thing, it works for sums. Now let's show it works for an integral. Okay, so take an epsilon greater than 0. Now I'm going to choose a particular partition. So this works for any partition. So I'm going to choose P such that I'm going to write this down first, and then I'll explain why this holds. I'm going to choose a partition P. I can always choose I can choose a partition P, knowing that my function f is integrable. I know that I can choose a partition P so that my upper sums or lower sums are both within epsilon of the actual value of the integral. Okay. Well, this is a Riemann sum, but a Riemann sum always lives between lower sums and upper sums. So since I can always choose an upper sum, for example, that's within epsilon of the true value of the integral, or I could choose a partition such that the lower sum was within epsilon of that, I can choose a partition so that the Riemann sum, which is between those upper and lower sums, is within epsilon of the true value of the integral. All right. So again, I can choose, anytime somebody says choose this so that this condition holds, you should ask why. The answer here is because f is integrable. Okay. So because f is integrable, I can choose a partition P so that this Riemann sum minus this will be less than epsilon. But this means if I look at that sum is just what I have here, which is equal to f of b minus f of a. And this holds for all epsilon greater than 0. Okay, so forget about all the stuff sitting in here. This, whatever this is a real number, right? F is a function. A and B are numbers, right? This is real number minus this value of this integral is a real number. So what you have here is that the absolute value of some real number is less than epsilon for every epsilon greater than 0. There's only one real number that holds for. That's 0. So since this inequality holds for all epsilon greater than 0, this thing sitting inside here must be equal to 0. But that implies that f of b minus f of a of this portion must be equal to this portion as desired. So the fundamental theorem of calculus, right, relates essentially this Riemann sum to this difference, and this all happens through the use right in this step of the fundamental theorem, or sorry, of the mean value theorem. So again, I want to highlight here that the differentiation piece really comes here through the mean value theorem, right? This just looks like a Riemann sum, but we relate it to this difference here via the mean value theorem. Okay. Now, again, the mean value theorem is, I think it's a theorem that when you first see it in calculus, it seems maybe you can do some problems with it, but it's not maybe incredibly useful. It is an incredibly useful theorem in analysis, precisely because it allows you, I mean, you typically see it in sort of this form that looks like this. But again, just simply by multiplying, what it allows us to do is think about the change in a function, in actual values of a function, as a change in the inputs times a particular value of the derivative, right? And that's really what is helping us right here. We're looking at sort of how does the change in this antiderivative function, right? How does that relate to over here, a change in the inputs times particular derivative values of this antiderivative function? Okay. So again, so incredibly helpful and useful theorem in all sorts of different areas of math and all sorts of different sub areas of analysis. So we'll stop this video here. In the next video, we will look at a generalization of the Riemann integral called the Riemann-Stieltjes integral. And we'll see that not only does it generalize the Riemann integral, but a lot of the same properties hold for the Riemann-Stieltjes integral that held for the Riemann integral. So we will first look at a definition of the Riemann-Stieltjes integral. We will explore some properties of it, and then actually towards the end, we'll actually connect it back and see that in some special cases, you can actually calculate the Riemann-Stieltjes integral by just calculating an appropriate Riemann integral. And once we've done with that, which again will take several videos, but once we're done with that, that will conclude our discussion of integration for this course before we move on to sequences and series, both of real numbers and of functions.